Okay, with this, we're going to continue our discussion of probability, but now we're going to shift gears a little bit. And we're going to change from the situation where we have a discrete random variable, where counting or calculating probability is counting the number of times an occurrence happens out of the total number of outcomes, to looking at what happens when any possible value over an interval of numbers can occur. This is called continuous probability. We're going to look at two things. We're going to look at what's called the uniform probability distribution. We're going to use that then as an example to help us define what we mean by a probability density function. And then we're going to move on to talking about the most useful continuous distribution called the normal. So first of all, in this lecture, we're just going to discuss the uniform probability distribution. As an example, suppose that you are expecting a package to occur or to arrive, and that you are told that that package will arrive somewhere between 10 a.m. and 11 a.m. And we're going to look at it in terms of minutes. Okay, so the package could arrive at time 10, or it could arrive any time before 11 a.m. So we're going to let 10 be 0 minutes passage, and 60 be the number of minutes that have passed at 11. So any time between 0 and 60 is a possible time for that package to be delivered. Any moment in time in that hour is equally likely to occur. So this is called, when this happens, it's called the uniform probability distribution. Whenever we have a situation where each value over an interval is equally likely to occur, it's called the uniform probability distribution. In general, if we have something, a continuous random variable, we can talk about probability for that continuous random variable by looking at what's called the probability density function. Similar to what we did earlier with the probability distribution, the probability density function gives us a way of calculating probability, but for a continuous variable instead of a discrete variable. It has to have two specific properties, though. One, the function itself must be greater than or equal to 0. And two, the total area under the curve must equal 1. The reason the total area under the curve must equal 1 is that we are now going to associate probability of an event occurring with the area under the curve that is associated with that event. Area can never be negative, so we know we're going to have something greater than 0, but I also want to have all 100% of possibilities accounted for, so that's why I want the area under the curve to equal 1. In the example that we have, with the uniform density function, the curve that we get is a horizontal line. Each value over the interval is equally likely. So we start our number line from 0 to 60, and we set a horizontal line in there to represent the probability density function. That PDF has a height of 1 over 60. It's going to be a constant value because this is a uniform distribution. How do I know the height is 1 over 60? Well, I know that the width of this rectangle that I've drawn is 60. I need the area of the entire rectangle to be equal to 1. So in order for the area to be 1, I need to multiply 60 by 1 over 60 to get an area of 1. So that's what tells me the height. Outside of that, there is no height to the curve because I know it's not going to arrive before 10 a.m. I know it's not going to arrive after 11 a.m. So those aren't possibilities that can occur. So there is no, the value of the function is 0 outside of that interval. Whenever you have the uniform density function, your picture for that will end up being a rectangle. The width of the rectangle will be represented by the time interval, or the interval over which the value can occur. The height of the rectangle will be 1 over that interval. So now let's say that we want to calculate probability over some subinterval. Calculate the probability and arrive somewhere between 15 and 20 minutes, for example. Well, what I need to do is calculate the area under the curve, under that graph, over the interval for which the probability represents the event. So, for example, let's say I want to find the probability of being between 15 and 30 minutes. Well, I can draw in the interval from 15 to 30, and I can map out the area that goes along with that. And notice what we have is this rectangle right here. We have the 15 to 30 as my time on this, and the height of that rectangle then represents the area under the curve between 15 and 30. In the uniform distribution, it's always a nice rectangle. So to come up with probability, it's a matter of calculating the area of this rectangle. The width of the rectangle is 15. The height of the rectangle is 1/60th. So the area is 15 over 60, or 0.25. So again, with a uniform distribution, probability is always going to be working with areas of rectangles. In general, if I have a uniform distribution that is uniform over the interval to A to B, I get this rectangle where the width is from A to B. The length of that rectangle then is the distance between B and A, which is B minus A. So the height of the rectangle, in order to be of area 1, has to be 1 over B minus A. And if I'm going to look for probability that the variable is between two other numbers, C and D, I can plot those both on my number line here. I can then draw the rectangle that is associated with being between those two numbers up to the top of my rectangle, my bigger rectangle. The probability then that I am between C and D then is the area of this rectangle, which would be D minus C over B minus A. Again, with a uniform distribution, area under the curve is always going to be area of a rectangle. So the area of those rectangles will provide me the probability of an event occurring. One thing to note here is that if I were to try to look at the probability that X was a specific point in time on this interval, it would equal 0. Why would it equal 0? Well, the rectangle would have no width. If I went from C to C, it would be 0 over B minus A. I have to have some width in order to get an area. So one thing that's different about a continuous distribution than a discrete distribution is that each individual point has a 0 probability of occurring. But if I start looking at the probability of being over an interval, I get a width that I can work with and actually find an area under a curve. So that completes our discussion of the uniform distribution. Next, we're going to talk about the normal distribution, and that will be in the next lecture.